Okay, just now we have learned how to write down the bordered Hessian matrix for equality constraint problems. And now we want to extend the idea when you have a mixed constraint situation. In other words, now your objective function is subject to a collection of both equality and inequality constraint. Then in this case, how do I write down the bordered Hessian matrix? It turns out the way to write it down is essentially identical, okay? But I need to firstly pick a point first. So I'm going to pick a point that satisfies the first order condition. So let me write down here. So let P be a point that satisfies the first order condition, okay? And then, as before, we're going to write down two numbers here. So m and n. So n is identical as before. N is the number of variables of your objective function. Of the objective function f. Okay? Then what's m? M is a little more subtle. So it's not the total number of constraints, but the total number, so this is very important, the total number of equality and binding inequality constraint. Inequality constraint. At P. So in other words, when you form the bordered Hessian matrix, you throw away all the inequality constraints for which P is not binding there. Okay? Then in this case, the bordered Hessian matrix, the bordered Hessian, is still a m plus n times m plus n matrix. Okay? A bordered Hessian at P. Okay? I just emphasize at P. But how is that defined? So it turns out H, okay, let me write it down here. So H is defined essentially identical as before. It's defined as a matrix m plus n by m plus n matrix that come in four parts. This part is identically 0. The top left hand corner is identically 0. And how about this part? This part is formed by rows, okay, that are given by the gradient factor of the constraint function. But this time, you only look at the constraint function coming from the equality constraint and binding inequality constraint. So let me write it down. So this part, this is formed by the gradient of equality and binding inequality constraints. Okay? And then the right hand bottom corner, this part as usual, this is given by the Hessian matrix of the Lagrangian. Okay? And then this part, okay, this part is basically by taking transpose or by refracting along the diagonal, you get this part. So this part is essentially putting all the rows here as columns, okay? So this is how you form the bordered Hessian matrix. It's essentially identical as before. The only difference is now you have include all the constraints that are binding, okay? And you throw away all the inequality constraints that are not binding. So let us look at a concrete example. Consider the maximization problem. And then now the maximization problem concerns our objective function f that equals to x times y times z. And then you subject it to four inequality constraints, namely x plus y plus z less than equal to 3, and all the x, y, z are non-negative. And now you're given a point, okay, 1, 1, 1, 1, 0, 0, 0, is a solution to the first order condition. and write down the Bordered Hessian matrix at this point. So the first thing I'm going to write down is the Lagrangian, because I know I need a Lagrangian to form the Bordered Hessian matrix. So the Lagrangian, okay, equals to L equals to the objective function x times y times z minus lambda 1 times the first inequality constraint, so x plus y plus z minus 3, and minus lambda 2. So don't forget, because this is a maximization problem, so you have to rewrite all this in the form minus x less than equal to 0, minus y less than equal to 0, and minus z less than equal to 0. So you put minus x, minus y, and minus z respectively in your Lagrangian. So this is how you form the Lagrangian. And now you want to look at this particular point, okay? So in particular, at this point, xyz equals to 1, 1, 1. So xyz equals to 1, 1, 1. So note, add xyz equals to 1, 1, 1. Which constraint is binding? If you look at this 4 constraint, which one is binding? X, y, z equal 1, 1, 1. Oh, x plus y plus z equals to 3. So this one is binding. But all this 1, 1, 1, okay, these are not binding. So only the constraint x plus y plus z less than equal to 3 is binding. Therefore, in this case, M is the number of equality constraint and binding inequality constraint. But because I've no equality constraint, I've only one inequality constraint that's binding. Therefore, M is 1. Okay? And then N is the number of variables of my objective function, so 3. So the Bordered Hessian matrix is a 4x4 matrix, okay? So let us write down the Bordered Hessian matrix. Okay? So at this point, because only one inequality constraint is binding, so we expect when we form the Hessian matrix, only one gradient vector need to be put here, okay? And then we reflect it along the diagonal, so we got another column here. So let me write down carefully. Suppose I call this binding constraint function, I call it h. So I should put grad h here, and I put a 0 here, and I should put grad h here as well. And then what do I put here? Here, I put down the Hessian matrix of the Lagrangian function. So I put down Lxx, Lxy, Lxz, and the Lyy, Lyz, and Lzz. And because it's symmetric, once you write down half of it, you can write down the other half, xy, xz, and then yz. So it should be symmetric along the diagonal. Okay? So let's write down more concretely. So this is 0. Grad h. So h is x plus y plus z. If you take the gradient, I will get 1, 1, 1. If this 1, 1, 1, then this is also 1, 1, 1. Okay? So I just put the gradient vector as rows and column respectively. And here, I need to compute something, okay? So I need to compute the second order derivative of the Lagrangian function. So first, the Lxx. If you look at this carefully, you realize that if you differentiate every single term by x twice, everything dies, okay? So basically, this is 0. Similarly, you have 0, 0. Because you don't really have any y squared term. Therefore, or z squared term. Therefore, the second order derivative with respect to x, y, z will be 0. Okay, how about differentiate with respect to x and then y? Differentiate this with respect to x and then y, you get z. But then you realize that every single other term will die. So you get z here. And then xz, similarly, when you differentiate this term with respect to x and then z, you get a y. And then any other terms, because there's no second order term here, so they all die. So you get just x. Oh, sorry, you get just y, sorry. And then similarly, this x. And because this is symmetric, once you get half of it, you can get the other half for free. So you get z, y, and x. Okay? But this is not the end, because you're concerned about the bordered Hessian matrix at this point. When x, y, z, lambda 1, lambda 2, lambda 3, lambda 4 equals to 1, 1, 1, 1, 0, 0, 0. So at 1, 1, 1, 1, 0, 0, 0, what does this bordered Hessian matrix become? So these are numbers, I don't have to plug in. So what is that? X, Y, Z. So Z is 1, so I put 1 here. And similarly, X and Y are both 1. And then I have 1, 1, 1. And then finally, 2 zeros here. So this is the bordered Hessian matrix for at this point. The key thing is you need to identify how many constraints is binding in this case, and then that will give me the number m. And the n is still the number of variables of your objective function. And then the bordered Hessian matrix would be m plus n times m plus n matrix. So in this case, a 4 by 4 matrix. Okay? So writing down the correct bordered Hessian matrix is very important. And then on the next page, I will tell you how to use it to write down the second order condition.